Good morning, students. Today I am starting one more topic related to real numbers, decimal representation of rational numbers. We have studied in earlier class. Since rational numbers have two types of decimal representation. So this says that each rational number can be represented in two forms of decimal expansion. One is terminating decimal expansion and other is non-terminating repeating decimal expansion. So there are two concepts related to decimal expansions. First is, if x be a rational number such that x equal to p upon q, we are well aware each rational number can be expressed as p upon q, where p and q are co-prime. They may be integer also, are co-prime, and q can be expressed as q equal to the power m 5 to the power m. The denominator of this rational number, if can be expressed in the form of to the power m 5 to the power n, where m and n are whole numbers or non-negative integers, then x have terminating decimal expansion. For example, x equal to 3 upon 8. Here 3 and 8 both are co-prime, and 8 can be expressed to the power 3 into 5 to the power 0, because 0 and 3 both are the whole numbers. Okay? So 3 upon 8 have terminating decimal 0.375. Similarly, concept number 2, if x be a rational number such that x equal to a upon b and b cannot be expressed as to the power n 5 to the power n. That is the second concept. If denominator of the rational number cannot be expressed as to the power m 5 to the power n, where m and n again are whole numbers or non-negative integers, then a upon b have non-terminating repeating decimal. For example, x equal to 10 upon 3, both are the co-primes, but denominator of this number is 3 cannot be expressed as to the power m 5 to the power n, because in the prime factorization of 3 is also a prime number, so it cannot be reduced. So 10 upon 3 have non-terminating repeated decimal expansion 3.333 or 3.3 bar. Repeat number can be expressed by using the bar. Okay, thank you. Now I am discussing about some problem based on decimal representation of rational numbers. The question is, which of the following have a terminating decimal expansion and which have a non-terminating repeating decimal expansion? This question we can solve by now without using the long division method. So there are some rational numbers are given 3 upon 25, 6 upon 15, 63 upon 90, 6 upon 200, 29 upon 343, 13 upon 3125, 77 upon 210. So first work in this type of question is that first we reduce all the rational numbers into minimum co-primes. Okay? First question is that 3 upon 25. Here 25 can be reduced 5 5s and 5 1s. 25 have two factors, 5 into 5. This can be expressed 3 upon 5 square. That means 3 upon to the power 0, 5 to the power 2. So the denominator can be expressed in the form of to the power m, 5 to the power n. So 3 upon 25 has terminating decimal expansion. Second part of the question is that 6 upon 15. This can be reduced 3 to just 6, 3 5 to 15, 2 upon 5. Denominator can be expressed to the power 0, 5 to the power 1. So 6 upon 15 also a terminating decimal expansion. Again, we take fifth part of the question, 29 upon 343. 29 is the prime, so this cannot be reduced. But 343 can be reduced. 7, 49 ja, 7 7 ja, and 7 9 ja. So the denominator can be expressed 7 to the power 3. This cannot be expressed in the form of to the power m, 5 to the power n. So we know that well. This rational number has non-terminating repeating decimal. Now we are taking some more problems in this part. (63 upon 90). Third part of the question. 63 upon 90. This can be reduced. 9 7 is 63, 9 10 is 90. Here 7 upon 10 can be expressed 2 into 5 to the power 1, 5 to the power 1. So 63 upon 90 has terminating decimal. Now I am taking one more problem, seventh part from this question. 77 upon 210. This also can be reduced. 7 11 ja, 7 13. Okay. Now 30 can be split. 2 15 ja, 3 5 ja, and 5 1 ja. So this can be expressed 11 upon 2 to the power 1, 3 to the power 1, 5 to the power 1. Here denominator cannot be expressed in the form of to the power n, 5 to the power n. So 77 upon 210 has non-terminating repeating decimal. So these are some problems in which we check without long division method the given rational number is terminating decimal expansion or non-terminating repeating decimal expansion. Thank you. Now I am taking some more problems based on real numbers and the topic decimal representation of rational numbers. Without long division method, convert following rational numbers into terminating decimal expansion. Some part of the questions are given here, so we solve these questions without using the long division method. 3 upon 8. The first part is 3 upon 8. This can be written as 3 upon 2 the power 3. This also can be written as 3 to the power 2 the power 3, 5 to the power 3. In such a way, then only 2 to the power 3 is available. We multiply by 5 to the power 3 in numerator and denominator. So this can be written as 3 into 125 upon 2 into 5 whole power 3. That means 375 upon 10 to the power 3. So our first object is that we convert the denominator in the power of 10. Now 10 to the power 3 shows that this can be written as 0.375. So this is the decimal expansion of 3 to the power 8. Second part of the question is that 13 upon 125. Here this can be written as 13 upon 5 to the power 3. Again, this can be expressed 13 upon 5 to the power 3, but 2 is not present there, so multiply by 2 to the power 3 with the same power of 5. Multiply to the power 3. So here 5 to the power 3 is present in the denominator. So we multiply by 2 to the power 3 in numerator and denominator. This can be expressed 13 into 8 upon 5 into 2 whole power 3. That means 104 upon 10 to the power 3. This also can be written as 0.104. Third part of the question is there 7 upon 80. 7 upon 80 can be written as 2 to the 4 to the 8 to the 16 to the 5. That means 7 upon 2 to the power 4, 5 to the power 1. In the denominator, 2 to the power 4 and 5 to the power 1 are present. But we want to convert the denominator in the power of 10. So we can be express this 7 upon 2 to the power 4. The highest power of 2 is 4. So 5 also can be expressed as 5 to the power 3 into 5 to the power 3. We want to same power of the 2 as the power of 5. So multiply by 5 power of 3 in numerator and denominator. This can be written 7 into 125 upon 2 into 5 whole power 4. That means 7 5 ja 35, 7 2 ja 14, 3 17, 7 1 ja 7 8. 875 upon 10 to the power 4. Now the denominator, that is the power 4 of 10. So this can be written as 0.0875. This is the decimal expansion of 7 upon 80. Now I am taking fifth part of the question, 2 upon 25. This can be expressed 2 upon 5 square. That means 2 upon 5 square into 2 square. We want to equate the power of 5 and 2. So numerator can be written as 8 upon 5 into 2 whole power 2. That means 8 upon 10 square. So this can be 0.08. So these are some problems in which you want to convert without using the long division method into terminating decimal expansion. So, okay, thank you. Now one more concept. If decimal expansion of any real number is neither terminating nor repeating, then it is not a rational number. Okay? If decimal expansion of any real number is neither terminating nor repeating, then it is not a rational number. The first example based on this concept, if any real number can be expanded as 0.33333, that means this is a rational because it is repeated decimal. Second, 42.10, 100, 100, 100, 1 4 times 0 and so on is not rational because neither terminating nor repeating. Again I am taking one more problem, 31.321478, 321478 add on. So it is rational because it can be written as 3.321478 repeating. So this is a repeated decimal expansion. So this is also rational. Now I am taking one more hot question based on real numbers. Topic: decimal representation of rational numbers. Show that there is no positive integer n for which under root n plus 1 plus under root n minus 1 is rational number. That means the question is saying that we have no positive integer due to which this particular number is rational. So we solve this problem by the contradiction method. Solve. Let square root of n plus 1 plus square root of n minus 1 is rational. Then there exists a and b integer a and b such that a upon b equal to square root of n plus 1 plus square root of n minus 1, because each rational number can be expressed in the form of a upon b. This can be written as b upon a equal to 1 upon square root of n plus 1 plus square root of n minus 1. Rationalize b upon a equal to under root n plus 1 minus under root, this is the equation number first, under root n plus 1 minus under root n minus 1 upon under root n plus 1 plus under root n minus 1 into under root n plus 1 minus under root n minus 1 due to rationalization. Next step become b upon a equal to under root n plus 1 minus under root n minus 1 upon n plus 1 minus n plus 1. This become 2b upon a equal to under root n plus 1 minus under root n minus 1. This is equation number 2. Now 1 plus 2. Add the equation 1 with equation 2. So now we have a upon b plus 2b upon a equal to under root n plus 1 plus under root n minus 1 plus under root n plus 1 minus under root n minus 1. After LCM we have a square plus 2b square upon ab equal to under root n minus 1, under root n minus 1 cancel out. So we have twice of under root n plus 1. This can be expressed a square plus 2b square upon twice ab equal to under root n plus 1. This equation can be assumed equation number A. I am repeating again from there. Suppose that under root n plus 1 plus under root n minus 1 is rational, then there exist integers a and b where b not equal to 0 such that a upon b equal to this, because each rational number can be expressed in the form of a upon b. Take reciprocal, so b upon a equal to 1 upon root n plus 1 plus under root n minus 1. Rationalized, so multiply by root n plus 1 minus root n minus 1 cross numerator and denominator. We have b upon a equal to this, 2 is in the denominator, so cross multiply we take here 2b upon a equal to root n plus 1 minus root n minus 1. Adding equation 1 and equation 2, we have a upon b plus 2b upon a, right hand side is this, cancel out from this. Now we have 2 under root n plus 1, 2 is coming denominator, so a square plus 2b square upon 2ab equal to under root n plus 1. Now second minus first. Now we subtract equation first from equation second. So we have 2b upon a minus a upon b equal to root n plus 1 minus root n minus 1 minus root n plus 1 minus root n minus 1. So now root n plus 1 is cancelled out here. After LCM, 2b square minus a square upon ab equal to minus 2 square root of n minus 1. This implies that a square minus 2b square upon 2ab equal to under root of n minus 1. This equation assume as equation number 3. So equation is a square plus 2b square upon 2ab equal to root n plus 1. Here this particular value of left hand side is rational number. Similarly, in this equation number b, left hand side is confirmly rational number. So from equations a and b, root n plus 1, root n minus 1 and root n plus 1 are rational numbers. Because left hand side are rational, so right hand side also. This implies that n minus 1 and n plus 1 are the perfect square of positive integers. Under root n minus 1, under root n plus 1 are rational, and if these values are rational, and confirmly n minus 1 and n plus 1 are the perfect squares of positive number. That means n minus 1 and n plus 1 take the place of 1, 4, 9, 16, 25, etc. Because if we take at the place of n minus 1, n plus 1 other than the perfect square, the values become irrational number. So n minus under root n minus 1 under root n plus 1 are rational number. So therefore confirmly n minus 1 and n plus 1 are the perfect squares of positive integer. But this is not possible. Why? What is the reason behind it? N minus 1 and n plus 1 are the perfect square of positive integers. Because we know that where the first perfect square is 1, second is 4, so difference is 3, third is 9, so difference of 4 and 9 is 5, next is 16, so difference is 7. So confirmly, but according to this, if we take this number 1, then this becomes 3. If this will be taken 2, so this becomes 5, because between n minus 1 and n plus 1, the difference is 2. So there is no possibility these type of two numbers become a perfect square. Are you confirmed? The difference of n plus 1 and n minus 1 due to difference of n plus 1 and n minus 1 is 2, and 2 perfect square never be differed by less than 3. So root n plus 1 plus root n minus 1 is not rational. I am repeating again. Left hand side of equation A, right hand side of equation A, both are rational numbers. So right hand side also rational numbers. So under root n plus 1, under root n minus 1 and under root n plus 1, both are the rational numbers. If these are rational numbers, then n minus 1 and n plus 1 are the perfect squares of positive integer. But this is not possible. Why? Due to the difference of n plus 1 and n minus 1 is 2. If these are the perfect square of integers, then this is not possible because the two perfect square never be differ by less than 3. So under root n plus 1 and under root n minus 1 is not the rational number. Thank you very much.